In this video, we're going to be doing some application and modeling problems involving trig functions. In this first example, we have a safety regulation states that the maximum angle of elevation for a rescue ladder is 72 degrees. A fire department's longest ladder is 110 feet. What is the maximum safe rescue height? So in this particular instance, we see our triangle that is created here that we're looking at. So that is our triangle. Given that, we have an angle of interest here of our 72 degrees, which is the maximum angle of elevation for our rescue ladder. We know that the ladder, the longest ladder, is 110 feet, as we can see here. This is our hypotenuse. So that would make this our opposite side. So our opposite side is the side that's next to the building. And then our adjacent side is side B. So given this information, since we want to know what is the maximum height that we can rescue somebody from, we're looking for this distance right here. Let's do this with a different color this time. So this will be our opposite. And this is the height that we're looking for. What's that maximum height that we could rescue someone? So here we're looking for the opposite, and we have our hypotenuse. So this would make a great sine function. So the sine of 72 degrees equals our opposite, which we don't know, so we'll call that side A, and our hypotenuse, 110. So to solve here, we're going to go ahead and multiply both sides by 110, which allows us to cancel out those 110s. And so we'll see that our maximum safe height is going to be 110 times the sine of 72 degrees. Plugging that into our calculator is going to give us approximately 104.6 feet, which would be our maximum safe height for rescue. Let's take a look at another problem. In this problem, at a point 200 feet from the base of a building, the angle of elevation to the bottom of the smokestack is 35 degrees, and the angle of elevation to the top is 53 degrees. We want to find the height S of the smokestack alone. So in this problem, we're going to see a couple different pieces. Here we have an A value. So that's our A value. And we have our smokestack. So here we have our smokestack, which is our S. We see a couple different angles. So here we see our angle that is the 53 degrees. And here we have our 35-degree angle. So we're going to be dealing with two different triangles. And we see that we have a base of 200 feet, and our right angle is right there. So there's our right triangle. And again, we have two of them. So in this situation, sometimes it's helpful to draw the two triangles. So we have our tall triangle, which has an angle of 53 degrees, a base of 200 feet, and a height of A plus S. We also have a triangle, or smaller triangle, which has an angle of elevation of 35 degrees. It still has that base of 200, and its height is just A. So now that we have the two triangles, we can see a little bit easier that we have the opposite sides and the adjacent sides for both sets of triangles, in which case we would want to use the tangent. So we're going to set up a tangent for each of our triangles. So we'll first take the tangent of our small triangle. So we have the tangent of 35 degrees equals our opposite over our adjacent. Then setting up the tangent for the larger triangle gives us the tangent of 53 degrees equals our A plus our S, which is our opposite side, over our adjacent side of 200. Now we want to try and get our variables by themselves. So we're going to begin by multiplying both sides by 200, which then gives us that A equals 200 times the tangent of 35. And on our other triangle, we'll do the same step. We'll multiply both sides by 200. Oops, let's switch colors. To cancel those out, which is going to tell us that A plus S equals 200 times the tangent of 53. So from here, we see that we know what A is, right? A is this 200 times the tangent of 35. So we can take that and put that in this A's spot. So we're going to take this and we're going to plug it in. So we're going to take that 200 times the tangent of 35 and put it into the A's spot. Now we want to try and get the S by itself. So we are going to subtract the 200 times the tangent of 35 from both sides. So that allows us to cancel that out. So we get that S equals 200 times the tangent of 53 minus 200 times the tangent of 35. We can't just subtract them because the 53 and the 35 aren't the same. So we'll need to take this and plug all of this into our calculator. So right now, what we're seeing is the exact answer, but we're looking for a real life estimate. So we want to have a value. So we're going to estimate this. So we're going to plug this in, and this is going to give us that S is going to be approximately 125.4 feet. So our smokestack all by itself is approximately 125.4 feet. Let's do one more example. In this example, a swimming pool is 200 meters long and 12 meters wide. The bottom of the pool is slanted so that the water depth is 1.3 meters. So again, the water depth is 1.3 meters at the shallow end and 4 meters deep at the deep end. So we're going to find the angle of depression or angle of the degrees at the bottom of the pool. So remember the shallow end said it was 1.3 meters deep at the shallow end. So here's the shallow end, which is 1.3. So if we create a rectangle and we come across here, then that means this portion would also be our 1.3, leaving us with the remainder as our triangle that we're looking at. So here's a side of our triangle, and here's a side of our triangle. So here we know that it's a total of 4 meters deep in the deep end. So altogether it's supposed to be 4 meters. And we know that part of it is 1.3. So if we take 4 and we subtract the 1.3, That's going to give us 2.7 as what's left for our triangle. Now our angle of depression is the angle created from our 90-degree side, from our adjacent side to our hypotenuse, which is marked here in purple. So we're looking for that angle. So if we look at our sides, that tells us that we have the opposite side. And don't forget that we were told that our swimming pool is 12 meters long. So 12 meters long. So we also have our adjacent side. So if we have the opposite and we have our adjacent, that would make a great tangent. So here, the tangent of our angle theta is going to be our opposite side, which is 2.7, over our adjacent side, which is 20. So because we're trying to find our angle, we're going to left multiply by the inverse of tangent, which allows us to cancel out that tangent, separating the theta. So the exact answer is going to be the inverse tangent of 2.7 divided by 20. But if you told somebody that the angle of depression was the inverse tangent of 2.7 divided by 20, they might look at you a little bit funny. So we want to know an actual estimated answer. So when we plug this into our calculator, that gives us an answer of 7.69 degrees. And that is our solution. So the angle of depression of that pool is 7.69 degrees.